Hello everyone. In this video, I'm going to explain two example problems related to fracture toughness and design to prevent fracture. We will discuss key concepts and equations such as fracture toughness, K1C, that I will explain that what is one and what is C, the meaning of that, plane strain, fractures, toughness, and how engineer use these values to ensure that structural components will not fail under stress. By the end of this session and this video, you will understand how to determine whether a material will fracture under a given load and how to find the maximum allowable crack length for safe operation. Okay. In this slide, we want to talk about the plane strain fracture toughness, or KC. When the sample thickness is much greater than the crack size, for example, you can see crack size here. The measured fracture toughness becomes independent of the thickness of the samples. In this case, the conditions called plane strains means other geometry means 2D or 2 dimensions are so greater and bigger than the thickness size, so we consider these as plane strain condition. This leads to what we call plane strain fracture toughness, represented by K1C. This is 1, not I is the Greek number. That mode 1, as you see here, is opening or tensile mode of crack surface displacement. You see other modes here, for example, at mode 2, sliding mode, and mode 3 means tearing mode. Okay. As I told you, 1 refers to mode 1 or crack displacement. Mode 1 is the opening or tensile mode, meaning the crack surface are being pulled apart by tension. It is the most common critical mode that we considered in fracture toughness, and because the most real cracks tend to open under tensile stress. The values of K1C are generally high for ductile material. C is abbreviations of critical here, means the fracture toughness, mode tensions, and the critical value of that. So KIC are generally high for ductile materials since they can absorb more energy before fractures, and is low considerable to ductile material for brittle materials which fail suddenly with little deformation. K1C is the most important design parameters in fracture mechanics because it gives the most conservative estimation. It represents the lowest toughness value, ensuring that the design remains safe even under the most constrained loading conditions. So we will talk about these values in next slide. When designing for preventing fractures, the main goal is to keep the stress intensity below the material's fracture toughness. Here you see that K1C is the fracture toughness. Y is the constant that usually for plane strain we considered 1. Sigma C means the critical stress. Root pi is the number, and A is the length of the crack. So when designing to prevent the fracture, the main goal is to keep the stress intensity below the material's fracture toughness. If the stress intensity reaches the fracture toughness, the crack becomes unstable and the material can fail. In the first scenario here, you see we have two scenarios in designing. You as a designer or mechanical engineer that doing designing. If K1C and the size of the crack or A specified. In this scenario, we are looking to finding the maximum or critical stress. Critical stress, it should be K1C divide Y root pi A. If you see here, means that if for each A and for different K, I see that it is the property of the material. For different material, we have different K1C. You see that when sigma C more than these limitations, fracture will happen. In second scenario, K1C and stress level or sigma specified, we know about that, and it dictates the maximum allowable size for the crack, means we can find AC. Again, it is the border of that. If AC more than this, for example, at this sigma, A less than this AC, everything is safe and the component be in safe condition. If we B more than this, as you see, fracture will occur. Okay, here we have two problems. The first problem, we have a sample 4340 steel alloy having a plane strain fracture. Toughness, what is this? It is K1C, 45 megapascal root meter, is exposed to a stress 1000 megapascal. Is it critical? We don't know. Only we know that it is under these loading conditions. Will this sample experience fracture if it is known that the largest surface crack is 0.75 millimeters? What is this? It is the crack length, or A. Why or why not? Assume that the parameter Y has a value of 1. I told you that in a previous slide that sometimes for plane strain scenarios, we can consider Y equal 1. But if it didn't say anything about that, we have to find Y before other step of calculation. Okay. So in this problem, ask us to determine whether this steel 4340 will fracture when exposed under the 1000 megapascals. We have the K1C and we have the Y and we have the A. So everything is clear for us. Only should be the first scenario. First scenario would be finding sigma C, and it is sigma C. So sigma C is K1C divide Y divide the root pi times A. We substitute that instead of Y1 and instead of A is the crack length here, and we find that, oh, critical value for sigma is 927. Now, what should we do? We should compare the loading condition to the critical stress. If loading conditions or loading stress more than critical stress, definitely the component or the sample will fail. Therefore, the fracture will most likely occur because this sample will tolerate the critical stress or maximum 927 megapascals before fracture, which is less than the applied stress of 1000 megapascals. So this problem was the first scenario, according to the first scenario. For the second problem, a structure component is fabricated from an alloy that has a plane strain fracture toughness, or K1C 45 megapascal root meter. It has been determined that this component fails at a stress of 300 megapascal. What is this? When say fails, definitely it is sigma C. So it is sigma C. When the maximum length of the surface crack, so A is 0.95 millimeter, What is the maximum allowable surface crack length in millimeter without fracture for this or same component exposed to a stress of 300 megapascals and made from another alloy? So it's very important. I told that K1C depends, it's a kind of material property. So for different material, we have different fracture toughness. With a plane strain fracture toughness of 57.5 megapascal root meters. So K1C for the second material is 57.5 megapascal. And for the first material, K1C for the first material is 45 megapascal root meter. Okay. But this problem didn't say anything about why. What should we do? At first, we should find the y value, yeah? So for the second problem, a component fails under a known stress when the surface crack reaches a certain size, and we want to determine the maximum allowable crack length for similar component, but made from an alloy with higher fracture. Why? Because you see that the fracture toughness for the second material is 57.5 megapascal compared to 45 megapascal. What should we do here? We know that AC is 1 per pi, K1C, sigma times Y squared, yeah? But what should we do here? We have AC or length of the crack. We have sigma C or critical. We have fracture toughness, K1C. Only things that we are looking for that is Y, but we don't know why. So when K1C is the plane stress fracture toughness, sigma applied stress, and Y is a design parameter using data for the first alloy. We have K1C, AC, and sigma. It is possible to calculate the value of Y. How we can find the Y equals K1C divided sigma per root pi times AC. By calculating that, we can find Y. We use this Y. Why we can use this Y? Because the stress condition or loading condition not change, so we can consider, and Y is the parameter, is the related loading condition, not the material property. So we can use this value as Y, and the maximum crack length for another alloy can be determined. We have the sigma, substitute here, we have Y, we have K1C for the second material, substitute here, and we find the length of crack. This highlights the key strategy for designing to prevent fractures. Engineers can ensure safety by limiting what the first one is applied stress. If you decrease the amount of the applied stress, you can avoid or prevent to reach to fraction. The second one is the controlling flaw size or crack size or A by through the regular inspections and maintenance. The third one, selecting material with higher fracture toughness, and it should be K1C. So the material that has fracture toughness that has be higher will be more good candidate for avoiding and preventing to reach to fracture. And another things, avoid the sharp corner or notches that amplify the stress. You know that at the tip of the notch or sharp corner or change the area or something, we have the concentrated stress. So we should avoid this. Understanding these principles allows components to remain under safe condition and safe loads and resist crack propagations and operate reliably throughout their service lives. Okay, I hope this video helped you understanding fracture toughness, plane strain fracture toughness, and how to design components to prevent fractures under two scenarios that we talk about that. As a special thank you, I have created a free study guide with everything we covered in this video today. To get your copy, just click the link in the description below. Your feedback helps me improve this lesson. So leave any comment if you have any questions. And don't forget to subscribe so you will not miss upcoming videos on topics like mechanical property, dislocation, fatigue, and other important material concepts that is important for you as a mechanical engineer. Thanks for watching and bye-bye.